This is section 2.2, chemical reactions. So all life depends on energy being transferred from one organism to another. And we have the law called the law of conservation of energy that states that we can't create energy and we can't destroy it. So therefore it has to be conserved and it has to be recycled from one organism to the next. What we call potential energy just means stored energy. So for example, in food, that stored energy is actually in the bonds in the food. And then what we call kinetic energy is energy that in motion or energy being used. So an example of this would be in our bodies. The energy used by our muscles called ATP to help us move, that would be kinetic energy. So stored energy versus energy in motion. And chemical compounds can be created from molecules, or we can actually take a compound and break it down into its separate components. So a chemical reaction is usually shown using what we call a chemical equation. This is an example on the bottom of the screen here of a chemical equation. All the reactants, or what goes into the reaction, can be found on the left side of the equation. So in this case, it's that CO2 and the H2O. And then the products, or what comes out of the reaction, are found on the right side. And in this case, it's C6H12O6 plus that 6O2. So this equation down here is actually the equation for photosynthesis. We're basically saying carbon dioxide and water, 6 molecules of each of those go into the equation, and with a little help of sunlight here, that arrow means yields, we get C6H12O6, which is simple sugar, and some oxygen, 6 molecules of it. So you'll have to learn that equation and memorize it later in the photosynthesis unit, but for right now it's a good one to just kind of show how we set this equation up. So all chemical equations have to be balanced, which means the same number of atoms that go in have to come back out. So if I put 12 hydrogens in, I have to bring 12 hydrogens back out. That goes with the law of conservation of matter that's saying we can either create or destroy matter. So it can't just disappear on us. If we put it in, it has to come back out. And this picture down here, this graph is showing what we call activation energy. It's the amount of energy we need to start a reaction to actually get it going. And that's why it's up so high here. But once we hit that threshold, once we actually get enough energy, our reaction will take place, the reactants will start colliding and interacting with each other, and then our products will come out the other side. These two examples are just some simple equations. What I want you to do is actually label the reactants and products on each side, and then tell me how many atoms are on each side. So actually list it out. Hydrogen, there's this many on the left, and oxygen, there's this many, and do the same for the right to figure out if it's balanced. If it's not balanced, you'll need to actually figure out what numbers would go there to help you balance that. So pause the tape for a minute, see if you can do this on your own. All right, so hopefully you've had a chance to do this. I'm going to label the reactants in red. Reactants are always on the left side of the equation. Let's do products in blue. Those are always on the right side. And then it wants you to list out how many atoms are on each side. So we'll start with the top one here. For hydrogen and oxygen, we have 2 oxygens, and you have to multiply these two numbers. So 2 times 2, you actually end up with 4 hydrogen on that one. Let's go over to this side. We have, again, 4 hydrogen, 2 times 2, and then you have to pretend there's a little imaginary 1 there. So 2 times 1, 2. So we have 4 hydrogen, 2 oxygen on each side. This equation is balanced. Okay, let's go to the next one down below. Carbon, hydrogen, and oxygen on each side. And we'll have to see how many we have here. So to start on this side, we have 1 carbon, 4 hydrogens, and 2 oxygens. On the right side, we have 1 carbon, 2 hydrogens, and 2 plus that imaginary 1, we have 3 oxygen. So this equation definitely is not balanced. We're going to have to fix it. And the easiest way to fix it would be to start putting some numbers in front of here. So I want to get this hydrogen balanced out. So if I have 4 on the left and I need 4 on the right, I'm going to actually pop a 2 in front of there. So that 2 now times 2 will change this to a 4. So we've got the carbon and hydrogen balanced out, but now that oxygen is a little bit of an issue. And that actually changed that to, oops, my smartboard's not working here. Erase that. So now if I look, I've got 2 times 1, that's 2, plus my 2, I'm up to 4 now on this side. So I've got to go back over to the left and fix that. So you put a 2 in front of this one, 2 times 2. Now fix this one to 4. So now we should be all balanced out. Everything's looking good. And these were just a couple quick examples of how to balance some equations. When you actually get to chemistry, it'll be a little bit more tricky than this, but we'll just kind of practice with some easier ones and figure out how to make both sides even out. And that's it for the section 2.2 notes.